All right, so let's go ahead and look at this example. So for part A, if we want to find f of 0, we want to see where does 0 fit in our domains. And we see that 0 is going to fit that top inequality because 0 is a value in between -2 and 1. So we're going to plug 0 in the place of x in that function, which makes 0 plus 3, which makes the output for that function 3. When we input 1, 1 satisfies the middle equation, but there's nowhere for me to plug 1 in the place of x, so the output for that is going to be 5. And then if we want to find f's value at 10, since 10 satisfies the bottom inequality, we plug 10 in the place of x, we get -10 plus 2, which is -8. Okay, so secondly, we want to sketch the graph of the function. Again, I want to start from left to right. So what I'm going to do is when we have a compound inequality, like we do for the top function, I want to get the function values at the two endpoints of the inequality. Okay, so I'm going to plug -2 into the top function first. So when I plug in -2, we get -2 plus 3, which is 1. So that means that that graph is going to contain the point -2, 1. I use a closed dot at that value because my inequality symbol is less than or equal to. Okay, so that's going to be a true statement. That is a point on the graph of my function. Okay, I next plug 1 into the function. When I plug 1 in, I get an output of 4. I'm going to use an open dot at the point 1, 4 because 1 does not satisfy that top inequality. Because that function is linear, I'm going to draw a line connecting those 2 points, looking like so. Okay, when x is equal to 1, the y value is 5, so that graph is going to contain the point 1, 5. Okay, so I'm going to draw that point on the graph. And then when x is bigger than 1, I'm going to graph the function -x plus 2. So again, when I have a standard inequality, I'm going to plug that first value, 1, into that function. So we get -1 plus 2, which makes the ordered pair 1, 1 on the graph. And I'm going to use an open dot at that point because 1 does not satisfy that bottom inequality. Okay, then I'm just going to pick a value bigger than 1. Let's say I pick 2. When I input 2, the output is 0. Again, I'm going to use a closed dot at that point because 2 satisfies that inequality. Okay, 2 is larger than 1, so that point has to be on my graph. And because that function is linear, I'm going to draw a line connecting those 2 points. Okay, so again, part C, if we want to find the domain, you can either look at the inequalities and equations here in that red box, or you can look at the graph. It doesn't matter. But when you see what x values get covered up by the graph, the smallest x value on the graph is -2. We're going to bracket that because that point is on the graph. And all the x values get covered up until we get to x is equal to 1. There is a point on the graph at x is equal to 1, and all the x values get covered up that are bigger than 1. So that's going to go from the half closed interval from -2 to infinity. If you want to write that in set notation, that would be the set of x such that x is greater than or equal to -2. I don't care. Either one of those notations will be acceptable there. Okay, for part D, find the intercepts. Let's do the x-intercept first. So where does the graph touch or cross the x-axis? It looks like it happens at the ordered pair 2, 0. And if we want to determine where the graph touches or crosses the y-axis, it looks like it happens at the ordered pair 0, 3. Okay, when we look at the range, we want to look at what y values get covered up by the graph. Okay, so again, we want to start from the smallest y value and then work our way up to the biggest y value. So like when we look at this part of the graph here, The smallest y value that's going to get covered up by that part of the graph is negative infinity. And all the y values are going to get covered up until we get to 1. But when we look over here at this point, there's a point on our graph at y is equal to 1. And all of the y values are going to get covered up until we get to the y value of 4. Okay, but since y is equal to 4 is not on the graph of our function, we have to use a parenthesis to open that interval. But we're not done yet because we have this additional y value at y is equal to 5 on the graph of our function. So we would have to union that interval with the single value of 5, and then again, you put a single value in set braces. Okay, so that's what the range would look like in interval notation. If you want to write that range in set notation, that would be the set of y such that y is less than 4 and y is equal to 5. So that's what the range would look like in set notation. Okay, I'm going to have you guys do one more of these. Okay, so go ahead and get number 3 copied. 3 is the piecewise function. The piecewise function f of x defined as 3x plus 1 when x is less than or equal to negative 2. It's defined as 4 when negative 2 is less than x, which is less than 4. And it's defined as rad x when 4 is less than or equal to x, which is less than or equal to 9. Okay, so part A asks you to sketch the graph of f. Part B, find the domain. Part C, find the intercepts. Part D, find the range. Okay, so go ahead and pause the video while you work on that. When you finish, go ahead and unpause, and then we'll take a look at the answer together. Okay, so we're going to sketch the graph of this to start with. So to start, I'm going to, because I have a standard inequality on top, I'm going to first start by plugging negative 2 into the function. Okay, so when I plug in negative 2, we get 3 times negative 2, which is negative 6, plus 1, which is negative 5. So that's going to be the ordered pair negative 2, negative 5. And because our inequality symbol is less than or equal to, we're going to use a closed dot at that value. And then I'm going to pick a number smaller than negative 2. Let's say I pick negative 3. When I input negative 3, the output's going to be negative 9 plus 1, which is negative 8. So we're going to go to negative 3, negative 8, which is down in here. Use a closed dot at that value, and then we're going to draw a line connecting those 2 points like so. Okay, then we're going to look at the values in between negative 2 and 4. Okay, so when the x value is negative 2, again, we have a compound inequality. We're going to take the 2 endpoints, plug them into the function, and see where the outputs are going to be. Well, because that function is constant, there's nowhere for me to input those values. So for the x value of negative 2, the y coordinate is going to be 4. And we're going to use an open dot at that point, negative 2, 4. And then for the x value of 4, the other endpoint, the y value is also going to be 4. So we're going to use an open dot at that value as well. And then because that function is constant, we're going to draw a horizontal line passing through those 2 points. Okay, next we want to graph the bottom function. Okay, so again, we have a compound inequality for that. I'm just going to plug the 2 endpoints into the the 2 endpoints of the inequality into the function. So when we plug in 4, the output's going to be the square root of 4, which is 2. So we go to the point 4, 2. because our sign is less than or equal to, we're going to use a closed dot at that value. And then I'm going to plug 9 into the function. The square root of 9 is 3. Because our sign is less than or equal to, I'm going to use a closed dot at that value as well. And then I'm going to draw the shape of the square root function connecting those 2 points. So that's going to be kind of a curve looking like so. Okay, so let's find the domain. So what x values are going to get covered up by the graph? Well, the smallest x value on the graph is negative infinity. And then all the x values from negative infinity to negative 2 get covered up by that part of the graph. But then we have all the x values from negative 2 to 4 get covered up by this part of the graph. And all the values from 4 to 9 get covered up by this part of the graph. So our domain, I'm just going to write it in interval notation here, is going to be the half closed interval from negative infinity to 9. Okay, the intercepts. The only intercept that we have here is a y-intercept, which occurs at the point 0, 4. There are no x-intercepts for the graph. Okay, that graph is not going to touch or cross the x-axis. Okay, and then lastly, the range. We want to go from the smallest y values to the biggest y value on our graph. And again, I'm just going to write this in interval notation only. Okay, so the smallest y value on our graph is over on this part of the graph here to the left. So that's going to be negative infinity. All the y values get covered up until we get to negative 5. Okay, and negative 5 is a y value on our graph, so we're going to bracket that. And then we're going to union that. The next smallest y value on our graph, I'm going to do this in black, occurs over here at y is equal to 2. And all the y values are on the graph until we get to y is equal to 3. Okay, so that's going to be the closed interval from 2 to 3. But we're still not done because we have this part of the graph in green that we haven't accounted for yet. Okay, and the y values on that part of the graph is the y value at 4. So we're going to union that with that single number of 4, which we write single values in inside of set braces. That's how we write single values in interval notation. Okay, so those are some good examples. Number one, not only getting us to sketch the graph of piecewise functions, but be able to identify certain features like the domain, range, and intercepts on the graphs of functions as well. Okay, last thing for us to talk about are even and odd functions, and we're going to do that in the next video.